Hello and welcome to the Applied Deep Learning course. In today's lecture, we're going to take a look at neural networks, optimization, and backpropagation. Before we dive into the topic, I would like to briefly recap on what we talked about last week. First thing was the difference between artificial intelligence, machine learning, and deep learning. And the second question I would like to briefly recap is what are the main ingredients for machine learning? If you want, pause the video here for a few seconds and try to answer those questions for yourself. On the terminology, I've given you the term artificial intelligence, which I believe is mostly a marketing term, and basically any knowledge-based system could be considered artificial intelligence. I personally would refrain from using this term because it's quite unclear what actually is intelligence and what artificial intelligence therefore is. However, there are things that are clearly defined, like machine learning, which is using data to answer questions, and linear regression is one example. Another one that I think is really nice is a k-nearest neighbor classification, where you just take a look at your data to answer questions about a previously unseen example. If you are extracting an efficient representation, and for example with neural networks, then we're talking about representation learning, and actually linear regression is also a representation, so maybe the example here is not the best one. But if we have neural networks that have a certain depth, then we usually talk about deep learning. How can machines learn? I gave you 3 ingredients that are essential here. Number 1 is the model, which is the set of computational rules that are needed to perform a certain task. A loss function, which tells you how good the model is doing on your data. And an optimization function that allows you to tweak your model to become better, to reduce the loss, to have ideally a very, very low loss. When we dive into these 3 things, we can start with the model, the computer, so to speak, that operates here. We typically have some data. For example, we have pictures of cats and dogs, and those images, for example, have labels. So we say this is a dog, this is a cat. And those inputs we typically feed into our model. So our model is the set of computational rules, and if we have images, color images, in this example, we would have a usually like 2-dimensional space for XY coordinates plus the RGB coordinates for the color information. So we have this 3-dimensional space here, and this is the input for our model, and then the model is asked to produce some output, some suggestion of what this could be. In our case, the probability of whether it's a dog or a cat. And once our machine has seen enough of these images during our training, we can ask it, okay, what is this thing? We can query and perform so-called inference on our model. So the first part here is what we call training, and the data that we use for that is the training set. And the data that the model has not seen during training is the test set. And in our case, it would then output maybe the probability that it's a dog, 70%, and the probability for this being a cat, 30%. If our model predicts probabilities, then we're usually talking about probabilistic models. But one question still remains. How does this work? How can a model perform a task on previously unseen data? If you think about it, if you learn French, you're not all of a sudden able to speak English. So how does this work? How does it work at all? And the answer for this is that we have a couple of assumptions for our data sets that need to hold in order for this to work. And the first assumption is that both data sets, the train and the test data set, must have a similar distribution. So training on English and then operating on French will not work. You will have to have something that shares the same underlying probability. So pictures of cats and dogs is kind of the same underlying distribution. The second thing that is important here is that the random variables that go into this are independent, so they don't influence each other. And those two properties are usually abbreviated as independent, identically distributed, IID. I'm sure you've heard this many times before. So those two things are requirements for this to work. And here is one example of a model that I trained in the past, where I tried to teach the machine to recognize the basic building blocks, the measures of the music scores. And the question was, will it generalize to other data? And in this example, it did not work very well. And the reason was because I trained it on black and white images, and then I gave it what you see here, these color images, and it worked okayish, but it didn't generalize very well. So you have to be aware of your data. In this example, the researchers tried to distinguish between different kinds of skin lesions, whether they are melanoma or benign. I think I gave this example already in the introduction. However, one interesting thing here was that the underlying data set was not independent and identically distributed, because for all the examples that they had in the data set that were melanoma, there was a ruler in the image, which is quite common to give doctors a bit more context about the skin lesion, how big it is, because if you just have the picture, you don't know how big it was. And the network that it trained became exceptionally good at this task. The problem, it didn't learn to distinguish between melanoma and benign skin lesions, it learned to detect rulers. The researchers found out that this was the underlying problem, because if you just removed the ruler, it always said it's benign, which obviously is not true. So they fixed the data and they retrained it, and then it worked much better. So be aware that your dataset has to have certain properties for this to work. When we talk about different classes of models, we basically distinguish between two broad categories. One, discriminative models that learn decision boundaries. So we're saying, okay, where is kind of the limit here? And then categorize this dot here as falling into the blue or the red category. The other category of models would be generative models that typically do not learn decision boundary, but class conditional densities, just some probability distributions underlying. The output of the model can also be classified depending on whether it outputs a finite number of different labels, of different outputs, say categories of cats, dogs, cars, which we would refer to as a classification problem, or a continuous output, in which we would talk about a regression problem, where we have a continuum of output values. Let's talk about neural networks. Neural networks have seen a very interesting development because they first were described in the 70s and really popularized back then. But the problem was back then the computational power to actually fuel these, and many of the approaches that we have nowadays did not exist. So as you can imagine, they didn't work very well, and there was so-called AI winter in the 80s, where basically no one was interested in neural networks anymore. And just, I think in the last 10 years, they became popular again with the advent of deep learning, and I think nowadays we can all agree that it's a very hypey topic. Artificial neural networks are inspired by the way how our brain works. And our brain works in the following way, that we have neurons in our head, and you can think of them as small computers that take inputs from other neurons through their dendrites, then perform some chemical computation. So the chemicals in there carry some electric current, and based on the inputs that it receives, the output is generated, and an electrical signal travels through the axon to other neurons. And this idea of how the biological neuron works was copied and try to replicate with a so-called artificial neuron. In our artificial neuron, we have a very similar structure. We have the body, which does some computation, and we have some inputs, our dendrites. In this case, you have x0, x1, x2 as input values, which are weighted by some values, w0, w1, 2. And you can perform a certain computation here. For example, you can sum up those values, add a bias term b, and then have an activation that says whether it should fire or not. And this is the output that will be fed into the next neuron. And the goal of the training would then be to find good values for this W and the bias term to produce something meaningful. For example, to find a line that separates two classes. These parameters that we're trying to find are the faders. They allow us to actually change how our model operates and whether it performs well or not. And if we have such parameters, we typically speak of parametric models. Non-parametric models are, for example, k-nearest neighbors, where you don't learn parameters, you just compare the data points to each other. Neural networks are parametric models, and they are controlled by the weight matrix W that we've seen before and a bias vector. And if you join multiple neurons, you create this whole parametric model that you can write like this. The activation function is also called nonlinearities, and it decides basically whether the neuron should be active or not. And the question is, why do we need an activation function? Why can't we just have this matrix multiplication, etc.? And the reason is that if we do not have any nonlinearities, we would basically just have a linear regression model. And if you think back for a second here about this formulation here, if you would not have this activation function, you would just have a matrix multiplication. And if you have multiple matrix multiplications, you can just combine them all into a single matrix multiplication. So your whole model would collapse into one single operation. The activation function prevents this and keeps the individual neurons, so to speak, separated. Popular activation functions that we encounter are the sigmoid, the rectified linear unit, short ReLU, or a leaky ReLU version. So the sigmoid function is, I would say, the most natural one, which is inspired by nature, by the way how our biological neurons work. The rectified linear unit is one that is very efficient to compute, but has certain downsides. If you imagine this figure here, you can see that it has like a very sharp edge at 0, and any input that would flow in here that is negative would just be completely eliminated. So this one has the problem that sometimes neurons tend to die. So eventually they will not fire anymore, they will not activate at all anymore. And people came up with the idea, okay, if this kind of hard cut to 0 is causing issues, maybe we can let a little bit of information through. And they came up with this idea of a leaky ReLU, which tries to mitigate this issue a little bit by still propagating a small signal in the negative domain. From a practical point of view, I recommend never use sigmoid. Usually try rectified linear unit as a default, and if dying neurons are concerned, use leaky ReLU or some other activation function. What are these other activation functions? This is actually still a quite active field of research, but at least two more recent activation functions I would like to present here. The first one is the sigmoid linear unit that you can see on the left here, and the other one is the Gaussian error linear unit, short CELU and GELU. And those activation functions have been shown to perform better than the rectified linear unit, and they're still quite easy to compute and have better properties. If you visualize the loss, the surface, you see that around the point 0, it's actually not a hard cut, but actually there is still a little bit of information that flows also from the negative values, which tends to help the neural networks to train better. As a general piece of advice, start with ReLU as one of the most simple ones, but also feel free to replace it with CELU or GELU as an alternative that can potentially help you to get even better results with just one line of code that is different, or 2 lines. A single neuron on its own is not really helpful. You cannot do much with it. However, when you take multiple neurons and connect them to each other, this is where the whole power of neural networks arises. And we speak of a neural network once we have this arrangement of neurons that are connected to each other. If you connect them in a specific way, that information only flows from one side to the other, we typically call this a feed-forward network. And those are the most popular neural networks that you will encounter. Neural networks are universal approximators, meaning that they can, in theory, approximate any function given the right training and the right data. And inside of such a network, we typically have neurons that share the same inputs. This group of neurons we would call a layer, and the input neurons would be the inputs. If you have multiple of these layers together in the middle of a neural network, we would call these the hidden units. And of course, you have the output neurons that actually produce whatever output the network should produce, say a class probability if you have a classification problem. If a neural network is a universal approximator, how do we get it to do the right thing? So the answer to that is that we typically try to structure neural networks and arrange it in a certain way to help the task and to make this a bit easier. And these architectures, we typically call one part of it the body, where we try to extract meaningful features, or where the neural network learns to extract features, and then depending on whatever problem we want to solve, we have the so-called head. This can be a classification head for a classification problem, or if we have a continuum, it would be a regression head where we try to produce continuous values. Let's talk about the loss function, aka the cost. I already mentioned it's basically trying to answer the question, how are we doing? Depending on the problem that we're trying to solve, different loss functions are required. Let's start with the mean squared error that you've probably seen many times before, which is typically used for classification problems. It computes the difference between yi, the target, and yi hat, the prediction, calculates the square, sums this up, and gives you one number in the end that tells you kind of how good it's doing. Similarly, you can use the absolute difference between two values, between the prediction and the underlying target, and those two losses are typically used when you have a regression problem. If you have a classification problem, we typically use the cross entropy loss, which looks the following. Don't be intimidated by this. Basically, it has two parts. One is kind of giving you a value for when you're right on the left side, and the other part is the penalty if the predictions are wrong. So this is what you would typically use when you have a classification problem. Let's put in some numbers to actually make this a bit clearer. So this is our formula, and here now we have two different predictions for the following target. You see that I have a classification problem and there is a so-called one-hot encoding. So I have 4 different classes, and whatever class is the true one will get a 100% probability that it's this class. And the predictions are now trying to mimic the same output. And obviously a good prediction would be something that has 0.01 for the first 3 classes and 0.96 for the correct class. And then we have a poor prediction which just guessed and said like every class is equally likely. If we put those two numbers in here, we're actually getting, for the good prediction, a loss of 0.04, and for the poor prediction, 1.39. Let's have a look at this in action. I'm now in my Google Colab, where I've already prepared the same things that we've just seen. So here would be an implementation of the cross entropy loss, where we can put in the predictions, the targets, and a small epsilon that we will use for numerical stability. You should see that it looks pretty similar to what we've seen before, and we're actually computing this not just for one prediction, but for a list of predictions. So we have this formula here, and now let's run this through with the predictions and the targets, and we're gonna compute the cross entropy loss here, which in our case is 0.71 for those two examples. If the first thing here now say becomes better, so let's make this 0, 0, 40 and 60. The total loss that we obtain for our entire prediction here, for all of the samples, has gone down to 0.27. Now let's make this thing like really bad. So it's quite confident, but it's actually the wrong one here, and see how this thing should actually now go up, 0.8. So the loss has gone up, and this is exactly what we're looking for. The big question now, once we have the loss function, is how do we get a low value for the loss function? And if you imagine having like 2 parameters, you can just try it. But once you have millions of parameters, this becomes an extremely challenging task. And one thing that you can actually do that helps us to get to a low loss is computing the derivative of the loss function. This derivative gives us a surface, a topology, and in this surface we try to get to a low point. So if you visualize it here, we would like to get down to the valley where the loss has a low value. So it's important that our loss function actually has to be differentiable in order to compute the derivative that we can try to get to a low point in the surface. However, the surface here can become extremely complicated. So the question is, how do we get to such a low value? And this is where our optimization comes in. How do we get to the valley of this loss surface? One extremely popular algorithm that is used as an optimization function is called gradient descent. It's a nonlinear optimization algorithm, and it's the most popular algorithm in deep learning. And the best way to think about it, or the easiest explanation that I've heard, is imagine that you're hiking in the mountains and you're trying to get to the lowest point. Well, you take a look and you try to find, okay, which direction you have to go, and then you start walking in that direction. However, there is one caveat. Think back of our loss surface. We don't just have like a 3-dimensional space, we have a million-dimensional space. So which way should I go? And the image that you have is basically knowing this is just not possible on a global scale. So it's like hiking with a bag on your head. So you don't see where the lowest point is in this high-dimensional space. However, what you can do is you can actually check your surrounding area. You can, do a 360 degree and check which part around you has the steepest descent. And once you found this, you take a small step into that direction. Once you took this small step, you repeat the procedure, and this is fundamentally how gradient descent works. Let f be a differentiable real-valued function, our loss function. Then you can compute the partial derivative of this f, xi of f, with respect to xi. So this encodes basically how fast the function f changes with xi. And the gradient of f is the vector of all partial derivatives of f. So basically it says, how fast does f change with all arguments at the same location. Now, if we know how the function changes with respect to all arguments at the same moment, we can actually compute the gradient as the first step to know where to go. And then we can actually take a step. And this is called the update parameter step, where we try to take a step into that direction. And the step size that we do here is called the learning rate alpha, which has to be a positive value. And as I said before, this requires that our loss function is differentiable and real valued. There are a couple of terms that are usually being used here, and one would be stochastic gradient descent, where we take a single example, compute the gradient, and then update our parameters theta with that gradient. Then there is batch gradient descent, where we would calculate the gradient for our entire data set and then perform an update step. Both things have the downsides. Stochastic gradient descent is usually very noisy, and batch gradient descent is computationally often not feasible because the data set is just too large. So the compromise here is typically so-called mini-batch gradient descent, where you compute the gradient for a small subset of samples, say 32, and you use that gradient to update your parameters. Why does it work? Because the loss is an expectation that can be approximated by a small number of samples. Some of the challenges that you typically have with this procedure is finding a proper learning rate. In other words, how big of a step should I take? Then whether you should use the same learning rate to apply all parameter updates, and of course potential critical points where your optimization could get stuck. I'm sure you've heard these terms before, global and local minima. So for our loss surface, we would ideally like to go to the global minimum, which would be the best one. However, we might not always be able to get there. And in deep learning, what we usually have is that there are multiple local minima which are good enough. So of course we would like to avoid some local minima where we're performing poorly, but typically what happens is that these critical points, we usually never get to those because we have so many parameters and we usually always find a way through our loss surface. So we typically don't arrive at these critical points, but we just jitter around on some low loss in the end. Another issue that you can have with this optimization procedure is that our loss function can have canyon-like curvature. So what happens is that your gradient bounces between those canyon walls. Imagine you're hiking and then you have a canyon here and you would take a really big step which would bring it exactly to the other side of the hill. What would you do there? You would turn around and go exactly the way back, and then you would kind of bounce back and forth. To combat this a little bit, there is a technique called momentum, where we kind of keep track of how fast we're moving in a certain direction, and whenever we shift the direction, we kind of slow down. So once we take multiple steps into the same direction, we accelerate and take bigger steps, otherwise we'll take smaller steps. So we update our velocity here, which is how fast we're moving, and then our parameter updates include this velocity parameter that helps us. It's also called Nesterov momentum, and it's typically what you should use with vanilla gradient descent optimization. There are also a couple of other algorithms for gradient descent, which are called adaptive algorithms, that have the benefit that they can kind of adapt to your data or can adapt the learning rate of specific parameters. For example, Adagrad adapts the learning rate to the parameters. So if you have some events that are very frequent, you have a lower learning rate, and for infrequent events, you use a higher learning rate. AdaDelta would be an extension of this, which also aggressively decreases the learning rate. RMS-prop was invented around the same time, and it's very similar to ADA delta. ADAM, it's one of the most popular adaptive optimizers, which adapts the learning rate and stores the decaying average of past gradients, which you can think of similar mechanism as momentum that we've seen before, and other things, for example, AMS, grad, which adapts the learning rate and also includes some historical information of past gradients. One thing I would like to point out is that some of these adaptive algorithms can absolutely outperform vanilla stochastic gradient descent, but the benefits of these optimizers are still controversial, and there are papers that claim that these adaptive algorithms are actually hurting. And yes, stochastic gradient descent might take longer, but the final result that you can get is better. So this is something that you should be aware of. But in order to understand, okay, which one should I use now? One personal recommendation is you can start with stochastic vanilla gradient descent with momentum, or use something like ADAM to see how it goes. And if you notice there are some problems, you can try another optimizer. Here you have a very nice visualization of different optimizers by Mr. Ruder. I really like it because it's a very nice visualization that shows how certain things work and how, for example, momentum bounces a little bit back and forth before it actually goes into the right direction. And stochastic gradient descent being like very slow to get down to the surface. Now that we've seen the loss function and heard about optimizers that we can use to optimize our model parameters, we still haven't answered the question how we can compute these partial derivatives, how we can compute the gradient itself. And the answer is backpropagation. We have our function, our loss function f, which is composed of other functions, and the whole loss function is a graph for which we need the derivatives. So what backpropagation does is it recursively applies the chain rule to compute the derivatives for this graph. And given that our functions that we use are usually quite simple, we can actually write it down. So if our function is a multiplication, addition, or a maximum, then these are our partial derivatives. So you can see it's quite easy to actually apply partial derivatives once we've broken down our loss function to the individual parts. For example, the partial derivative of f with respect to x1, if we have the multiplication, would be just x2. With respect to x2, it would be x1. If we have an addition, the partial derivative is 1. And if we have something like the max, you would need this if-else to decide whether it's 1 or 0. Let's have a look at an example to see this in action. This is our sample expression, a function e, that takes the values a and b, and we compute a plus b times b plus 1. So we have a and b as our inputs, and then we can visualize it in this graph. So we calculate c as the sum of a and b, and d as the sum of b and 1, which is then multiplied to obtain the value for e. So let's put in some numbers. A equals 2, b equals 1. Then you run it through and you get the value e equals 6. Now comes the interesting part. We ran some data through our network. Now we can compute the gradient. So we compute the local gradients independently. So we have our function e with respect to c. In our case, this was a multiplication. So we would take the other value, in this case 2. The partial derivative of e with respect to d would be 3. And then we have a couple of additions for which the partial derivatives are 1. Once you've computed these things, you can actually follow the graph down to compute the partial derivatives of e with respect to a by following this path through, which would be 1 times 2. And for e with respect to b, we would follow this path and add it together. So we have 1 times 2 plus 1 times 3, which would be 5. You might already see one of the problems that you encounter here is if this graph is such a toy example, you can easily sum up over different paths. However, if you have a huge graph, this becomes prohibitively expensive to compute. In other words, summing up over all paths would lead to this combinatorial explosion. So wouldn't it be nice if we can kind of factor this out and rewrite this computation to be able to just go through this graph and touch every node only exactly once. And this is what path factorization does. There are two techniques in path factorization. One is so-called forward mode differentiation, which tracks how one input affects every node. And the more interesting one that we're usually interested in for calculating the gradient is the so-called reverse mode differentiation, which basically tracks how every node affects one output. So we're looking from the output and want to see what effect each kind of node has. And the cool thing about this reverse mode differentiation is that it touches each node exactly once and it gives us the partial derivatives in one fell swoop, all the partial derivatives. In practice, deep learning libraries like TensorFlow or PyTorch have either an explicit graph representation or they have other approaches how they keep track of the functions that you calculate to perform this reverse mode differentiation. For example, PyTorch has a procedure called tape-based automatic differentiation. Summing up, neural networks are inspired by the way how the human brain works. They are parametric models where you put a weight on each input, and we have the so-called activation functions that introduce some nonlinearities to provide some kind of separation from each layer to each other, because otherwise all the matrix multiplications would just collapse into a single one. The models learn on our training set to predict samples from the test set, and it's important for the data set, for our underlying data set, that both things must have the same underlying distribution for the model to generalize well to previously unseen data. The loss function tells us how good we're doing, and we're computing the derivatives with respect to each parameter and then kind of updating all the parameters in one go, kind of taking a step towards that direction where our derivatives have the steepest descent. In other words, where we're going down the fastest. Gradient descent is an efficient way how we can navigate through this terrain by exactly performing this operation, by checking your surrounding area and then taking a small step into the direction of your steepest descent. That concludes today's lecture. I wish you a great day and see you soon.